Welcome back, everybody. So my name is Jérôme. So I will chair the session. So if you have questions, please put them in the chat, and I will ask them to Nigel. So the lecture is by Professor Nigel Cooper from Cambridge, and it's going to be about quantum dynamics and topology.
Okay, thanks a lot. So, well, it's a pleasure to be here. Thanks to the organizers for giving me the opportunity to be part of this very interesting school. And thanks to them for finding ways to make it work despite these restrictions. I'm delighted that I can be here. I'm sorry that not everybody else can be here, but please do interrupt and ask questions as we go through. Okay, so the title is very broad, quantum dynamics and topology. Those are two topics that have really occupied a lot of theoretical physicists over the last decade or so, and so there's really an enormous amount that one could say under each of those topics. Of course, I just have 3 lectures, and of course it's going to be very restricted. And the way that I'm going to restrict this is that I'm going to think about topology and focus on symmetry-protected topology, that is, topological phases that are short-range entangled. They don't have long-range, they don't have genuine topological order. They're simple symmetry-protected topological phases. And what's more, in order to try and be pedagogical, I'm going to focus on free fermions. But much of what I say can be extended also to interacting symmetry-protected phases. So the goal is really to discuss what we now understand about what happens when we take these symmetry-protected topological phases and go beyond the usual equilibrium situation, which is really a zero-temperature theory, the ground state of the system, by driving the system out of equilibrium and having unitary evolution, or in coupling the system to an external bath and having an open quantum system. So this is the plan for the lectures. I'll start with an introduction to topological band theory and explain what I mean by symmetry protection. That's really going to be an overview. I'll go through it as quickly as possible, but also trying to be pedagogical, set things up in a way that will be useful for the rest of the lectures. And that's going to be essentially what I cover in the lecture today. And then we'll go on to think about, next time, about Floquet dynamics, that is when we've got a time periodic Hamiltonian, and far from equilibrium dynamics, where you can think of as an arbitrary time evolution or a quench or something where there's no periodicity in time. And then finally, in the last lecture, well, we'll get on to open quantum systems. Okay, so that's where I'm going. And as I say, today I'm going to talk about the first section, which is topological band theory. And of course, this is just going to be a brief overview. If you want to find out more, there are many excellent reviews. The reviews by Hassan and Kane in RevMod Phys from 2010, and Shi and Zhang from in RevMod Phys in 2011. Oh, I should say that my own what I'm going to talk about is very general. It applies, to topological systems in many physical consequences, but actually a lot of the work that I've been involved in has involved cold atoms, and we have a review paper written here which covers a lot of the topics that will come up in the lectures. And so from this review paper you can find references to the papers that expand on the topics that I'll touch on during the lectures. So please look at that as a source of references. Even though it's mostly about cold atoms, the story is more general. Okay, so topological band theory. So I want to start with a few preliminaries, just a few quick preliminary thoughts just to set the stage before we get on to topological invariants for bands. And the first is to say, well, what we mean by a topological invariant. Now, of course, this has a well-defined mathematical definition, but I find it helpful to think also in physical terms, and to give an example, rather different to what we'll talk about mostly today, is a superfluid. So just as an example, imagine we have a superfluid in a ring geometry. So I have some sort of, this is meant to be some torus-type ring. We know that the superfluid we can write in terms, we can describe by some superfluid wave function, the square root of some superfluid density, e to the I phi of r. And we know when we have a system like this, that, we can classify different sectors of the superfluid flow in terms of the circulation of the superfluid around the ring. So here I've got some path running around the ring, and I can classify, or I can characterize different flows in terms of a winding number, which I call NW, which is 1 over 2 pi, the integral around this this path of grad phi dr. Okay, and this winding number is a topological invariant. It's unchanged under smooth deformations of the physical system. That's under smooth deformations of the superfluid wave function. We have to, of course, define what we mean by smooth. And here, smooth means that, well, phi has to be well defined everywhere, so we require that the superfluid density had better not be vanish. So the superfluid density is always non-zero on the path P, on which we're constructing this integral. So this was integral around that path. And the other comment I want to make is that quite typically these topological invariants have direct physical consequences. And in this case, there's a physical consequence, which is that there's a metastability, that if we have a circulating flow of this type with some non-zero change in the phase of the wave function around the loop, then it gives some metastable state, which carries a persistent current. So there's a physical consequence. It's a metastable persistent current. Okay. Now, for this topological band theory, we're going to discuss topological invariants defined in energy bands, not in real space, but in momentum space. And so my second preliminary is just to define, to remind you about block bands, and to set up, just to set up the notation that I'll be using. So here I'm thinking about a single particle, quantum mechanics of a single particle moving in some periodic potential. Let's say it's periodic in one dimension. The potential at x plus a is v of x. And then we know that the energy eigenstates of the system are, by Bloch's theorem, they're characterized by a quasi-momentum q, which lives on the Brillouin zone between here in one dimension is between minus pi over a and pi over a. And there are some energy bands which, well, there's some bands here which we can say are have got labeled by some index. The nth band has got some energy E n sub q for the wave vector q. And of course, because everything is periodic in this Brillouin zone, it's the same as q, well, q plus g, where g is one of the reciprocal lattice vectors defined by the spatial periodicity. Now, the eigenstates themselves can be written as the wave functions psi q of r are given by Bloch's theorem as e to the I q dot r times some functions u n q of r. So this is the nth band by Bloch's theorem, where these functions appearing here are periodic in space. There, r goes to r plus a, where a are the lattice vectors of the system. Okay. So the topological invariants that we're interested in, they characterize the wave functions in these bands. So the topological invariants characterize how these periodic functions, this u n of q, how these states, well, I can write them as a general state like this, vary across the Brillouin zone. And again, we have to think about, so these are topological invariants, so they're invariant under smooth deformations. So what do we mean by smooth deformations here? Well, essentially, what we require is that the states are remain well defined, and the smooth deformation is going to be that there's no gap closing. So one can imagine changing the Hamiltonian of the system or changing the potential in such a way that these energies will change, the wave functions themselves will change as you vary the Hamiltonian, but we don't allow any two bands to touch, and provided the bands don't touch, we say that we've made a smooth deformation of the system, and whatever topological invariant is constructed will remain unchanged. And these, there are also physical consequences. And the consequences that arise are essentially the existence of gapless edge states. So imagine that we fill, say, some number of these bands with electrons. So we fill this one, fill this one's empty. Then this is a bulk band insulator. There's an energy gap to excite an electron from the filled band to an empty band. So there's a bulk gap. But if the topological invariant or the sum of the topological invariants associated with the filled bands is non-zero, then there will be gapless edge states or gapless surface states. Okay. So that's what that sets up. Some of the notation. One thing to say is that I'm going to, throughout, I'm just going to set the periodicity A to be 1, so the lattice constant will be 1, and I'll also use h bar of 1. So, if they crop up, don't worry, but if they're not there, then it's because they're 1. Okay, and one last preliminary I want to remind you of is, because I'll make use of it in various ways throughout the lectures, is the notion of Berry phase. So here we're going to think about adiabatic variation of some parameter. So I've got some Hamiltonian which depends on some parameters x, some set of parameters written as this vector x. It could be anything, but it's just, or it could be some parameters that define the physical couplings. And we have some eigenstates, psi n of x, which has got energies En of x, psi n of x. And I'm, for now, I'll assume that the spectrum is non-degenerate. So these are all isolated energies and isolated eigenstates. And I want to think about the adiabatic variation of X. So we make an adiabatic change of X around some closed cycle. So I'll make an adiabatic cycle of X as a function of time from some initial time to a final time when X of t will be X of 0. So pictorially, I've got, let's say I had two parameters, X1 and X2. Then we'll start at time t is 0 at some set of parameters, and then in some state, psi n of X of 0. And then we change them slowly compared to the inverse spacing between levels so that everything is adiabatic. There are no transitions between the different states, and we come back to where we started from, so we have to come back into a state, well, whatever state we started from, psi n, comes back to the same state, psi n, up to an overall phase, and that phase has the dynamical part given by the integral of the instantaneous energy around the cycle. So, and it has this geometrical part, or Berry phase, gamma geo, where, so I should, for whichever band we're looking at, nth, or whichever state, n, and this geometrical phase is given by the line integral of the Berry connection around this, where the Berry connection, n, is I psi n d by dx psi n. Okay. Yes, please. No, X is just some set of parameters. So X is not the space coordinate. Here I'm just setting this up as sort of general. There's the general Berry phase analysis. Maybe it would be better to have called it lambda, just to make sure that there's no confusion. Yeah. So I have this line integral of this Berry connection, this effective vector potential that's appearing in the system, or we can write this as the integral over this surface bounded by this of the curl of the Berry connection. Let me just write it in. If we had 3 coordinates, we would have the curl of this integrated over this surface S, and where this quantity is the Berry curvature. Okay. So this is just general analysis of Berry phase, but we're going to make use of it one way or another throughout the lectures. Okay. So so with those preliminaries, I can now get on to start talking about topological invariants for these bands. So let me. I will start with the classic case of the two-dimensional band insulator. So this is following the classic work of Thoilus, Komoto, Nightingale, and Denice from 1982 in discussing the integer quantum Hall effect, where they showed that if you have such a situation of a band insulator where you filled bands, but you're working in 2 dimensions, then even though it's there's a gap in the spectrum, it's still not a normal insulator because it can carry a current, it can carry a Hall current with a Hall conductance. So it can have a non-zero Hall conductance, meaning that if we apply an electric field in the y direction, there can be a current density in the transverse x direction given by this response coefficient sigma xy, and they showed that sigma xy is given by E squared over h times the sum over the filled bands of 1 over 2 pi times the integral of the this Berry curvature. So this, well, I just write it again, curl of A of n d2q. So here, so now we've gone from taking this Berry phase in some abstract set of parameters x to now applying it in reciprocal space. So x is now being replaced by the wave vector, or the quasi-momentum, and so this Berry connection is defined for the block states of the nth band. So a n of q is I u and q d by dq of u and q. Okay. So this quantity appearing here with the 1 over 2 pi, this is now referred to as the Chern number, and it's an integer valued topological invariant. So you can see how you can understand why it's integer valued by thinking about the integral of this Berry curvature over the Brillouin zone. So I've got a 2-dimensional Brillouin zone with the qx and qy. I'm assuming it's got some rectangular symmetry, but of course that doesn't really matter. This integral of the curl was the integral of the Berry curvature over the Brillouin zone. We could also relate to an integral around the boundary of a line integral around the boundary. So I realize that red doesn't show up so well, so I just draw again this rectangle, but with the arrows around the boundary, and we would say that this what's relevant is this integral around the boundary of a dot dq. Now you might think that this is going to be 0 because after all the Brillouin zone is periodic both in qy and in qx, and so the integral along this line looks like it should cancel the integral along this line and also here. The integral around the entire Brillouin zone is the same as the integral over a zero area, but actually it's not 0. It's 2 pi times this integer, and it's not 0 because this vector potential a n of q has gauge-dependent singularities. Now the Berry curvature itself, as long as the bands don't touch, the Berry curvature itself generically will be smooth, but the vector potential, or this Berry connection related to that is if the Chern number is non-zero, this will have some singular points or vortices. And essentially, these vortices, counting these vortices, determines what this Chern number is. So to make that a bit more concrete, I want to go through one example. Just show an example for a system that we'll use again and again, which is a situation where we've just got two bands. So if you've got a two-band system, then I can write the block state U Q. Well, it was before it was a function of position, a continuous function of position. But if I just have a two-band system, it's just represented by the amplitudes on two sites in the unit cell, and it can be written as cosine of theta q over 2, sine theta q over 2, e to the I phi sub q, which is the same parameterization that Karel and Schoutens used for representing a two-level system. Here is just we have a two-level system at every point in the Brillouin zone, at every point q. So we can think of the u q for some band n. I'm going to suppress n in much of what I write, so please just not to have too many indices. But so let's not worry about it for now. But there's some state which is characterized by this angle theta of q, and its azimuthal angle with respect to some direction of phi of q. Okay. So if we have, in that representation, we can draw a picture of what a configuration looks like when it has a non-zero Chern number, which is that, well, we can draw, I can draw many things, but I'll draw one for a Chern number of 1, where I'll say that on the boundary of the Brillouin zone, that theta is 0. And I represent it by a vector that's pointing towards the North Pole, so it'll just be a point. Okay. And somewhere elsewhere in the Brillouin zone, the theta is going to be pi, so it's going to point towards the South Pole. I represent that by some plus sign. And as we go around that, the angle will change by 2 pi, make some vortex structure. So this unit vector on the block sphere will trace out some vortex around the South Pole and then come up to be at the North Pole on the boundary. Okay. So this is some smooth configuration of the system which will give rise to a Chern number of 1, and you can see that it's a situation where this unit vector wraps once over the sphere. So you can so that's one helpful picture to understand what the Chern number looks like in this two-band system. But we can also use it to see what I meant about these gauge-dependent singularities, because we can directly compute what this Berry connection is in this case for the state in terms of theta and phi. And if you do that, you'll find that A is minus sine squared theta q over 2 times grad phi. So this is something which, in the configuration I've drawn here, becomes singular around this vortex around the South Pole. So this is singular or discontinuous at theta q equals pi, because then sine squared pi by 2 is 1, and we have gradient of phi, but the phase phi, or the angle phi, is ill-defined at that point, because phi has a vortex, it changes by 2 pi as you go around this point. So this vector potential is not well-defined at that point, and therefore, whenever we went from taking an integral of the Berry curvature, which was smooth, and applying Stokes to represent it as a line integral, really what we should have done was to take the line integral, to say that the integral of the Berry curvature was the line integral around the external surface minus the line integral around an infinitesimal loop that's called P sub V at the center. So the actual, what was relevant is the line integral around, let's path P on the outside, dq, minus the integral P sub V of A dot dq. And this integral of grad phi times, well, minus 1 around this loop gives us plus 1. So, or plus 2 pi. There's a grad phi, because phi changes by 2 pi, this is plus 2 pi, and that will give us the Chern number of 1. Okay. But of course, this, this is something that we can, that's gauge dependent. We made a special choice that all of the phase entered into the second component here. We can multiply by an overall phase that removes that vortex from that point. But in order for the function to remain periodic in the Brillouin zone, we'll put a vortex somewhere else. So we'll always end up with one vortex, one singular point, and that singular point is responsible for the Chern number.
So can I ask a question? So,
please.
UQ depends on R, right? Depends on position.
Yes.
So theta Q and phi Q depend on position as well?
No, so this was, so here there was quite a lot hidden in that step. So I've gone from thinking of, here I'm thinking in real space about a particle moving in continuous space. So it's, the full Hilbert space is every position that it could have in a continuous position R. In going from here to there, I'm essentially making some type binding type approximation where I say that in a unit cell, there are two sites where the particle could sit. It either sits on an A-type site or a B-type site, let's say, and the amplitude to be in one position is this cosine theta over 2, and the amplitude to be the other is here. So really I should, let me write this out, that what this represents is that you, if I wanted to go back into position space, I would write it as UN Q of R would be cosine theta Q over 2 times some Vanier orbital phi sub A R R minus RA plus what sine theta over 2 e to the I phi times some other function phi b at R minus RB. So one is centered on sites around some site A, and one is centered on some sites B. But they're two different basis wave functions, and we're restricting the functions to just being linear combinations of these two basis wave functions. Thanks.
Can I ask another question?
Please.
So this non-zero Chern number is in general always going to be signaling the presence of these monopoles of the gauge field A.
Sorry, I didn't catch that. Very. Could you say it again? Maybe try and speak clearly into the microphone.
Is it always the case that the vector field A will have a singularity when there is a non-zero Chern number? So
yes, it's always the case that A. So the question, so it's always the case that this Berry connection will have some singular point when there's non-zero Chern number. That's right, because otherwise we could just sort of Stokes theorem transformation and integrate around something that if A was smooth, then we would zero just by expanding to this integral around the outside. So indeed, there has to be such a gauge-dependent singularity. This is something that also appears if you try and it was understood by Dirac in constructing the vector potential for a magnetic monopole, that if you wanted to have a uniform magnetic field coming out of some point of space, going through some spherical surface, then you have to, you can't have a smooth vector potential. There has to be some singular point, a so-called Dirac string, where the vector potential has a singularity. But this, the flux associated with that singularity is 2 pi, and it has no physical consequence, and you can move it around wherever you want. But you're forced to have such a Dirac string if you want to have flux emerging from a monopole.
Yes, thank you.
Actually, you have partially already answered to my question, because I just wanted to ask where does the gauge freedom come from? So my question was, why do you say that the field A is a gauge field? But so it's like an analogy with D1 gauge theories into dimensions.
Yes, it's an analogy with that, but it's also very explicit. I can just make a gauge transformation here. I can just multiply this by a phase, a global, phase which depends on a wave vector q, and that will, of course, that will make it a change to this connection. So I'll get a term which is proportional to the gradient of chi, but it will make no change to the Berry curvature.
Okay.
Yeah,
okay. Thank you.
Yeah. Okay, so it's, I'm sorry? Provided chi is not singular. Yes, that's right. Yes. Thanks. Okay, so let me say a couple of words about physical consequences. Let's see how. Okay. Good. So physical consequences. Well, one is that, well, I've already stated it. It has quantized Hall conductance, sigma xy is E squared over h times the Chern number. But here, really, the Chern number is the total Chern number. It's the sum of the Chern numbers for all of the bands that are filled. Really, at the single particle level, each band has got its own Chern number, Cn, and we should add up all of the ones that are filled. Okay. Associated with this, and what has been well known for many years, is that this Hall conductance can be associated with the existence of C gapless edge modes. So if we now think in real space, so now I draw a picture of the sample with a boundary in real space, then it's we filled up a certain number of bands. It's a bulk insulator, so in the center there are no single particle states that can propagate freely at the Fermi energy. However, on the boundary, there's some gapless edge mode that runs around in one direction. And this, the canonical picture from the quantum Hall effect, where we thought particles moving in a magnetic field, is that in the center, the particles are doing cyclotron orbits, just going around in circles. But when these circles hit the edge, they give skipping orbits that run around the edge in this chiral manner. So this that's one edge mode, but if the Chern number is C, we should have C such modes. And there's related to this, which is helpful when we think about non-equilibrium systems, is that these gapless edge modes also give rise to degeneracies in the entanglement spectrum. So you get degenerates, entanglement spectrum. And I'll come back to say a bit more about that later, well, hopefully later today. Okay, so that's this canonical classic example of a topological invariant for a band insulator, known for decades. It's quite special and specific, which is that it exists in 2 dimensions. And it also, as you can see from this, it requires time reversal symmetry to be broken, because this state, the fact that this runs in one direction and not the other, means that it can only be there when time reversal symmetry is broken, that is when you've applied a magnetic field or broken time reversal in some other way, for example, through magnetism. And so this, for many years, thought as a special case. But of course, the real interest from the notion of symmetry-protected topological bands was the discovery that there's a whole a slew of different topological invariants that arise once you account for symmetries. That's what I want to get on to now and say a few words, general words about symmetry-protected topological bands. Okay.
Well, so maybe this is a good time for questions, if
Yep.
there are questions in the chat or in the audience.
What is exactly meant by entanglement spectrum?
Well, so maybe I can ask a question. So,
Please.
well, so is it correct to say that you have constructed a map from from the torus to the sphere, and you're looking at the wrapping number?
That's right. So this picture here is that's right. Is the map in the case where it's the two-band system where the block states can be represented by this two-component states, and therefore they can be represented by a unit vector in 3 dimensions. Then we're mapping from the two torus onto the sphere, and these maps are generalized winding numbers. So just as at the start I talked about the winding number of a superfluid, that's a phase changing by 2 pi, or 2 pi times a winding number as you go around a circle. The map from a two-dimensional torus or indeed a two-dimensional sphere onto the surface of a sphere is also a generalized winding number that is characterized by an integer number of wrappings. Yeah, thank you.
So we have a question in the chat by Anwar Mustaj. So what is exactly meant by entanglement spectrum?
I'll define it. I'll define it when I come to it. But thank you. That's. Yeah.
Okay. Other questions? No.
Okay.
I have a question, actually, if I may.
Yeah.
So why are these edge states referred to as C gapless edge states? What does the C refer to in this case? Is it simply the Chern number, or?
Yeah, the Chern number, yes. So sorry, the C, the sort of curly C I was drawing is the Chern number. So indeed, the number of those edge states is the integer of the Hall conductance. So if the Hall,
it's a quantifier.
Yes, it's the integer. It is the topological invariant. It's the number that's like the winding number of the superfluid that tells us which topological sector you're in. And so that number is the integer topological invariant. It will remain equal to that integer provided the gap doesn't close. And so,
yes.
Thank you. Yeah.
Yeah, thanks.
Okay. Okay, so let me. Symmetry protected topological bands. And here again, I'm going to give just the flavor or the general idea, or what's rather than all of the details, because there's just not time to cover all. But the basic point, what I said before, where the Chern number was there for 2 dimensions, when you break time reversal symmetry, you can have topological insulators and indeed topological superconductors in all possible dimensions whenever you impose some additional symmetries on the Hamiltonian. So topological insulators or superconductors arise in all dimensions or I should say can arise can arise in all dimensions if symmetries are imposed. Okay. And there are various symmetries that one can consider, but the classic example, and the one for which is very generic and on which most attention is paid, is the set of generic non-spatial symmetries which were identified by Altland and Zernbauer in 97. So they were thinking about just random matrices, something where there was no spatial structure whatsoever, and classifying the different forms of symmetry that the Hamiltonian can adopt. And they found there are 10 cases. So this classification is sometimes referred to as the tenfold way. And the examples of this are, one classic example is if we've got time reversal symmetry in, well, 2 dimensions or 3 dimensions, but let's say I have in 2D, then if there's time reversal symmetry in 2D for spinful electrons, spin-and-a-half electrons, then there's a so-called Z2 topological insulator, which has the sort of real space picture that it has an edge state which is time reversal symmetric. So this is now my real picture, and instead of having one edge mode that goes, say, in the clockwise direction, I have one mode that goes in the clockwise direction, which could be spinking. You could think of it as the spin-up electrons moving in a clockwise direction. And in the counterclockwise direction, there's another gapless edge mode, which, loosely speaking, can be thought of as the spin-down electrons. And so under time reversal, this edge mode is time reversal symmetric because spin-up goes to spin-down and the directions swap. And so this is a time reversal symmetric pattern where we can have a gapless edge mode. So all of these topological insulators and superconductors are characterized by the fact that the bulk has got a gap, but the edge is gapless. And this applies for insulators and sort of filling bands, as I discussed before, or for conductors where the relevant Hamiltonian you think that's considered is the Bogoliubov-de Gennes Hamiltonian that also mixes particles and holes. So this leads to a series of states, which I'm not going to go through in detail here. I'm going to focus in most of my presentation in a simple situation of chiral symmetry described by a Su-Schrieffer-Heeger model, but I just bring up that it's part of this larger tenfold classification. There are, of course, other symmetries that one impose. One could impose general spatial symmetries like crystalline symmetries, and there's a whole the whole story of topological crystalline insulators as well, which also carry gapless edge modes arising from the existence of crystalline symmetries, as opposed to these non-spatial symmetries like time reversal. Okay, I just will say. So I'm going to, in the next part of the lecture, I will explain how you can get a topological invariant in the case where there's some symmetry imposed. But for now, I just want to say a few words about topological equivalence. In a more general, within a more general picture. So we can also think about the topological classification in terms of the adiabatic continuity of one phase with another. So we can imagine that we take the ground state of some Hamiltonian, which might be one which has got this edge state, and we could change the Hamiltonian slowly and ask what what states can we get into. And this adiabatic continuity breaks Hilbert space up into sections, those which are characterized by different topological invariants. So the notion is that we have adiabatic continuity of the many-body ground state under changes in the Hamiltonian, but now the idea is that if we've got symmetry-protected topology, we should have symmetry-preserving deformations of the Hamiltonian. So you've now got some Hamiltonian as a function of some set of parameters. Now X again is just some general set of parameters, but we need to have continuity without any gap closing. Because as I said, in the band picture, if the band's closed, then the topological invariant is lost. But if the gap stays open, then we can say that the states are continuously connected. And so we can think of this as defining some equivalence classes in the many-body Hilbert space, which, you know, this is now some abstract picture of Hilbert space where this section might be ones where the Chern number is 0. There's a part of Hilbert space where the Chern number is 1. And if we change the Hamiltonian, we can access all of the different states in here, which are all, we have got no Chern number and no edge states, or we can access all of the states here, but if we try to go from one to the other, then the gap has to close. And so we have some picture of a continuity between these states. And this is helpful because it allows us, in general, to extend the notion that we've been discussing so far about band insulators to situations where we don't have just a simple non-interacting band insulator. So we could have a disorder right? So there's no notion of a Brillouin zone anymore, but we can still have a notion of an energy gap, or we can even consider interacting phases of matter, and these are so-called interacting symmetry-protected topological phases, which can be interacting fermions, so where they would be closely connected to what we've been discussing so far, but they could in principle be bosonic systems. So the classes of topological phases of quantum spin systems fall into interacting SPT phases. Okay, I think it's a natural place where I'll stop. So I'll come back after the break and to give some more concrete example of the symmetry-protected topological band. And in fact, maybe I'll start by talking about the entanglement spectrum because there was a question about that. But let me stop there, and I'm happy to take questions now or after the break.
All right, so are there questions? So maybe I can ask a question. So shouldn't we consider translation invariance as preserving, as being a symmetry that is that we want to preserve, to have this classification based on Brillouin zones, on topology on Brillouin zones, or?
So yeah. So if I want to construct, most of what I say will be a case where there's translation invariance and there'll be a Brillouin zone. And so indeed, if we're constructing, if we want to construct things from the picture of Brillouin zones, we'd better maintain translation invariance. So that's certainly the case. Here, this one panel was meant to just to say how what I'm describing, how it can be made more general, in that everything I'm describing is for free fermions with translational invariance. However, under this notion of topological equivalence, meaning that the ground states are adiabatically connected, it would be possible to to break translational symmetry and still have a notion of topology and adiabatic continuity with, for example, this could be, there could be a subset of this which has got full translational invariance, and then it's connected to all of the states which have got, which are disordered. But we can also introduce interactions, and those interactions won't change the existence of these topological classification or of these gapless edge states. So you're right that if I want to construct topological invariance in terms of integrals over the band structure, that only applies for full translational invariance, but the notion itself can be extended beyond that to more general settings.
So yeah, this topological argument are basically single particle, no? Ones, because you always have. So what happens if you have some truly many-body system? I mean, how you can?
Yes. So I introduced it all as purely single particle. That's right. But I can, in principle, within this picture, I can imagine adiabatically turning on, let's say for fermions, I could start introducing interactions. Now, as long as the interactions don't close the gap, as long as the ground state remains uniquely defined, then let's say it's got churn number 1. If we turn on interactions and the gaps, it still stays gapped, but I've got an interacting many-body system with a gap that's continuously connected to the non-interacting system with churn number 1, then that interacting system will also have a gapless edge state and will be topological in the same way. It has the same. It will have it's the same phase. It's because it's adiabatically connected, it can be the same phase. And similarly, so that allows you to go much beyond this non-interacting system. But moreover, it also allows you, not that I'm going to say anything about it in these lectures, it does also allow you to extend to bosonic systems, right? So there, non-interacting bosons are completely sick and extreme, where they just sit in the lowest state. There's no notion of filling a band, but you can still use the same approach to define topological phases of bosons and classify them for different dimensionalities and different symmetry classes. And so that's the more general notion of symmetry protected topological phases should be interpreted as a fully interacting description both for fermions and for bosons. Thanks.
Regarding this answer that you just gave, are there physical consequences in case of bosons, such as I mean, in the case of fermions, you have these gapless edge states. But for bosons, what would be a physical manifestation of these topological phases?
So the question, if I understood correctly, the question is, what are the physical manifestations of these topological phases for bosons? And indeed, it can be the same qualitative statement that you can have a phase of matter which has got, in the bulk, it is gapped, or if you put it on a periodic geometry, then it has a bulk gap. But at the surface, there can be a gapless state that appears. And the classic example of this is the spin one chain, where there's a phase, the Haldean phase, which is a gapped phase in the bulk, but on the boundary each boundary, there's a spin-a-half degree of freedom, which is a exactly zero energy gapless state. And so the notion of the symmetry protected phase also has the same physical consequence that there's a gapless state associated with boundaries.
Okay, so it's similar physical manifestations.
Yes.
Okay, thank you.
Thank you.
So there are cases in which the tenfold classification breaks down due to interaction.
That's right, yes.
Because, I mean, not Z2, but in some other cases, you can think that boundary states interact and then become massive, And at that point, the massive bulk, massive boundary is a trivial insulator, and so.
Yes,
Yes.
so there is a, the interacting version for fermions is not identical to the tenfold way. There can be breakdown of boundary modes, and so some integer classifications can be reduced to Z8 or in certain cases. That's right. So it's not. So this. I should be more cautious here. It's not that the classification is not exactly preserved. We put interactions on, but the same structure can be applied. That's right. Thank you.
Okay, other questions? No? So, okay, so let's take the break now then, and we resume in, what, 5 minutes? 5 minutes? Okay. All right, so we start again.
Okay, welcome back. So, since I mentioned entanglement spectrum and there was a question, let me to that now just to define what it is and to say what the consequences are. So for the entanglement spectrum, one can apply this in any dimension, but I'm going to turn to some one-dimensional examples soon. So let's just think about some one-dimensional sample in real space, and I'll divide it into two pieces, which will be left and right. Okay, but I can just so I've got some bulk quantum system. I divide it into two regions, left and right. Then very generally, it can be decomposed into a sum over. So this so-called Schmidt decomposition. It can be decomposed with some positive weights, which I'll call e to the minus xi alpha over 2 times some state psi alpha that lives and some other state phi alpha that acts on the right, that lives on the right. So this is the so-called Schmidt decomposition of the many-body wave function into states which are partitioned between the two regions. Some coefficients here, the Schmidt weights, which can be thought of as probabilities that tell us about this decomposition. And from the taking the trace over the right of the pure state density matrix of the entire system, and this, well, this set of weights squared by left psi alpha. Okay. So these psi alphas are the eigenstates of the matrix. These are the eigenstates of the reduced density matrix and the weights. Okay. So the result, which I'm just going to quote, but it's a very that well, I was inspired by work of Lee and Haldane. They argued that this set of chi's, which can be thought of as a set of energies, and they argued that this set of energies reflects the edge state spectrum, the dynamical edge state spectrum of a bounded system. So this is actually something which is a system, but we've just made a cut in it in the description, and they argue that this has got some physical connection to the actual gapless edge spectrum. And there's a beautiful result from Fidkowski from 2000 that proved for free fermions. So if we've got, and let's say on the left there are m orbitals, so there are, the number of states is 2 to the m, because each orbital could either have no fermions or one fermion. So n orbitals in L, then he showed that the set of the entanglement spectrum, or actually really the set of weights e to the minus can be given as the set, I write it out, product of R is 1 to m, m's the number of orbitals, of 1/2 plus 1/2 s sub r lambda r for SR is plus or minus 1. Let me move this up. So so here, so R just runs over the m different orbitals that one can, they constitute this system in L. And then we take this product of some lambdas. So lambda R are some quantities which lie between 1 and -1. And they're, as I said in a minute, they're going to represent the edge spectrum. But just to understand this formula, we take the product over sets, all SRs of plus or minus 1. So there are 2 to the m different choices here. For each R, there are m values of R. Each of them I can choose +1 or -1. And I construct all of these, and we'll get 2 to the m eigenvalues of the density matrix, which are the which spans the entire space. So the set of these eigenvalues is given by this formula, where the physical content is only in these lambda r's. And what he showed is that these are the single particle energies of a related system of a in the same topological sector, a flatband model with a boundary. Okay. So the flatband model, in making connection to what I was saying before about this adiabatic continuity, we can think about taking, the model that we're interested in, and we could adiabatically change the energy eigenvalues. So it has some bands, they have some energies, but we can adiabatically change the energies, keeping the energy eigenstates, but change it to something where the occupied bands are all at energy -1, the empty bands are at energy +1. We can do that without ever closing the gap, so it must be in the same topological sector. And the fact that these eigenvalues lambda are precisely the edge spectrum for that model. So now a system with a physical edge. And so if we have if we've got a topological phase, then we must have one or more of these lambdas, lambda r's must be 0. And it means that when we think about this formula, there's going to be some degeneracies, because it doesn't matter whether SR is plus -1 when lambda r is 0, we get entanglement degeneracies. So this is a direct...
Sorry, so there seems to be problems with the audio, and apparently the problems are worse when you are too much on the left. So
okay.
Could you
okay.
try to,
with my hand.
Could you just try to stay as much as possible, because there's an antenna there, and apparently it doesn't work if you're too far on the left.
Okay.
Yeah.
Okay. Sorry about that.
Sorry.
Please. Okay. Are there any questions on that? I mean, I'll give an example of this in a. Now I'm going to turn to some simple physical example. I'll give an example of this in that case. But this defines what we mean by the entanglement spectrum. And I just quoted this very nice result, which shows that actually, even from the bulk, many-body wave function, a single wave function, you can learn something about the edge spectrum for the model, and one can characterize, one can have something like an edge spectrum, even though we're just looking at a single many-body wave function. Okay, Okay, so I want to talk about topological insulators in one dimension. So just to have a simple example of this symmetry-protected topological band insulators. And now, in 2 dimensions, we got a topological invariant by integrating the Berry curvature over the Brillouin zone. In 1 dimension, there's a natural thing one can try to do, which is to integrate over the Brillouin zone, minus pi to pi, to integrate the Berry connection. dq. And this is a quantity was introduced by Zach to characterize not just one-dimensional systems, but higher dimensional band structures, so it's referred to as the Zach phase. Really, it's the Berry phase you get as you go right across the Brillouin zone, and we're going to, in everything I talk about, I'll consider situations where we've made gauge choices so that the Hamiltonian and the wave functions are periodic in the reciprocal lattice vectors. Okay. So this, while one can compute this, but it's rather different from the Chern number, or the integral of the curl of the Berry connection, because this, in general, this can take any value you like. So there's no reason why this has to be an integer. The arguments I used before about why the integral of the Berry curvature over the Brillouin zone, that it had to be 2 pi times an integer, or and this Chern number, those just don't apply. In general, this can take any value you like. But the only way, so it's therefore will only be quantized. It only gives you a quantized topological invariant when there are some symmetries. So it's only quantized in the presence of symmetries. But I want to show an example of how that works, and how you can use it to define symmetry-protected topological invariant. Okay, and to the example I want to focus on is the Su Schrieffer Heeger model, which was introduced in 1979 to describe as an approximate model for polyacetylene, alternating single and double bonds of a carbon chain. And the picture, so I've lost my place. Yeah, so the picture is that we have a type binding model where we have a unit cell which has got 2 sites B. So we're going to have 1 unit cell which I'll label by integer j. And these A and B are coupled by some tunnel coupling, which between them in the unit cell has got j prime. Then from 1 unit cell to another, we call it j. And then everything repeats. Sorry, j plus 1. Okay. So this is, and then, and keep going. So I just think of a bulk of this type. Okay. The general wave function, I can write the sum over j of some amplitude to be on the A site, aj, plus amplitude to be on the B site, on the B-type site in unit cell j. Okay. But of course it has translational invariance, and so the energy eigenstates are states of definite wave vector q, so I can write them as UAB is characterized by some wave vector q, which is given by some amplitude, UABJ depends on some wave vector q, so at a position j, the phase advances as e to the I q times j, e to the I q j, where there's UAB of q. Okay. So there's some amplitudes. So I just have I describe the state with wave vector q is some 2-band system with amplitudes UA and UB of Q. And it's a straightforward matter to write down what the Hamiltonian is at wave vector Q to get what equations these amplitudes must satisfy. So it's, well, risking that I drop out, I'll stand over. So there's no energy offsets on the sides, so it's 0 in the diagonal, and then we get minus j prime minus j e to the minus iq, and minus j prime minus j e to the iq. So these describe the hopping in the unit cell with no q dependence, and the hopping from one unit cell to the next has the e to the iq dependence. Should I? Yeah. Okay, thank you. Okay, so since this I can write, well, there are various ways to write it. It's helpful to think of it as minus some vector h of q, scalar product with the Pauli matrices, and in these terms I'd write hx plus I hy is j prime plus j e to the I q. And I can also write this as modulus of the vector e to the I chi of q, the phase of it. Okay, so these are all just representations of that Hamiltonian. Okay, but in terms of that, it's straightforward to find the energy eigenvalues. There are two states, E plus minus of Q, which are plus or minus the modulus of H, and the spectrum in general gives us some two bands with a gap. It's symmetric about zero energy, and you know, if we have one particle per site, we'll fill this lowest band, and we have a band insulator. And it's a band insulator, except at one case, if J is equal to J prime, then the gap here will close. So gap closes at Q equals pi for J equals J prime. But otherwise, when J is not equal to J prime, it's a band insulator. So we have, okay, so that's it. What else? Oh, it's maybe helpful to write the wave functions. U plus minus of Q is 1 over root 2, 1, e to the I chi of Q, where chi is the phase appearing here. Okay. Okay. Yeah, please. Yes, this should be, I think it should be minus plus. Thank you. Yeah, right. Yeah, there are two states, and they're just the phases here. Yeah. Okay. So so we can take that and we can compute this Zach phase. Let's say for the lowest band, phi Zach for, well, I've had a superscript n for which band I'm talking about, and let's say it's a -1 because we filled the lower band. We can compute the just compute it directly, and what you'll get is that it's minus 1/2 the integral across the Brillouin zone of d chi by dq dq. So it's minus pi times a winding number, right? It's how many times does this phase chi appearing here, how many times does it change by 2 pi as we go across the Brillouin zone. And the value of this then depends on the parameters on j and j prime. You can see that pictorially if I represent this hx and hy, which was defined up here as a function of q. Well, there's a bit that's q independent, which is j prime. So I put it j prime here. And if I have j less than j prime, then adding this term on will add a little circle in the complex, a little circle. Well, this is like the complex plane because hy is the imaginary part of this complex number. So if less than j prime, then we'll get a circle of this type. And so as we change q goes from 0 round to 2 pi, hx plus ihy will trace out this trajectory in the complex plane. And so the angle chi of q will not wind, right? It'll start increasing and then it will decrease and come back to 0. So chi of q will just go slightly positive and then negative and back to 0. And so here you'll get that the winding number is 0. But if we consider a case j greater than j prime, let me attempt a different color. Then we have something. No, we have some. We'll draw a circle that looks like this. I hope people can see it online. If j is greater than j prime, then this angle will go around the origin and change by 2 pi. And so in this case, we'll get a winding number is 1. Here, the Zach phase is minus pi, and here, the Zach phase is 0. And so we get two different values. We get it quantized in units of pi by this winding number, and we also get this feature that we can't intersect these two without a gap closing. Because if we wanted to deform this circle into the red circle, it would have to cross the origin where mod h is 0, and when mod h is 0, that's j equals j prime, is where we get this gap closing. Okay. So these are two states that cannot be interconverted without a gap closure. So this plays the role. This looks just like a topological invariant as before. We've got this integer valued quantity, this NW, winding number, and it's stable under deformations provided the gap doesn't close. And indeed, this is the example I wanted to give of a symmetry protected topological invariant. So let me just say a bit more about why it's symmetry protected. So remember we had h is minus h of q dot sigma. Now the Hamiltonian we considered had a particular feature which it had nothing in the diagonal. So the sigma z term was vanished. That is, the hz is 0. And this gives, in the Altland-Zirnbauer classification, this is an illustration of a so-called chiral symmetry, where chiral symmetry is defined as a symmetry of the Hamiltonian matrix, and formally it's that there is a unitary operator. In this case, it's sigma z plays that role, which when you act on the Hamiltonian, well, sigma z and sigma z dagger are the same, but if it was a unitary operator, we would have u h u dagger is equal to minus the Hamiltonian and where the operator squares to the identity. So this is the Chiral symmetry of the outlier classification. And if you have this symmetry in the system, then you have a well-defined winding number, and you can see that in the block sphere picture. If we think in the block sphere, when hz is 0, then the case where we had j less than j prime well, basically this state always has an azimuthal angle of pi by 2, so it lies in an equatorial plane, and it's only the longitudinal angle chi that changes. So in one case, in the non-topological case, this white circle just traced out some trajectory on the equator that came back to itself. So that was phi zac is 0. But in the red case, it traced out some circle that went all the way around the equator. And as long as we restrict the state to lie on the equator, that is, we restrict hz to be 0, then we can't smoothly convert one to the other. So this red one is phi zac minus pi. So for hz is 0, we have we have the winding number providing a topological invariant. Okay. But you can see that if we were to break that symmetry, so if hz were non-zero, then we could take one of these and we could change the Hamiltonian in such a way that we deform this loop to start exploring something away from the equator.
Sorry, so apparently the red choke is not visible.
Okay, thank you. Okay, so the red was just saying that phi zac is minus pi. And what I've drawn in red is just a circle that runs around the equator, which is different from what I had in white, which was just something that was located around one point and didn't wind around the equator at all. But now what I'm trying to draw is that if we break the symmetry, so we allow hz to be non-zero, in principle we could deform the Hamiltonian in such a way that as a function of q, this loop starts to go up over the North Pole, and we would continuously connect one phase to the other without forcing h to be 0, that is, without closing the gap. So when hz is non-zero, the topological distinction is lost. Okay. So this is a nice clean example of what one can think of as a symmetry-protected topological invariant. As long as we have that symmetry, this Chiral symmetry in that case, we have an invariant and we can't deform one phase to another to change that invariant without the gap closing. But if we break that symmetry, the topological distinction is lost, and we can make continuous transformations from one to the other without gap closure. Yes? Well, so the question was, in this case, what is the Zach phase? Well, in this case, the Zach phase is just what it takes no special value. I started this lecture by saying that we can write down the Zach phase. There's no reason for it to be quantized except if there's a symmetry, and so in this case that symmetry can be viewed as restriction to the equator, and then we get pi times an integer. But in general, when there are no symmetries, the Zach phase can just take any value in principle.
So we have a question in the chat by Saz Chagrin David. So HZ is the diagonal values of H as in the Pauli matrix space?
Yes, that's right. Yeah. So HZ is exactly the bit from the sigma z of the Pauli matrix. So physically it would be an energy offset on the A and the B sides.
Are there other questions?
Okay,
so maybe I can ask a question.
Yes,
so I mean, earlier you defined the Chern number, and that turned out to be exactly a physical observable.
Yes.
Can you do? Is there something equivalent, something analogous for the Zag phase? Can you? Or?
So I'm not going to say much. The Zag phase can be related to a polarization, so an electrical polarization, and that measuring or defining polarization by itself is somewhat difficult and can be ambiguous. But one way, which will come up later, is that one way in which you can detect it is that if there are changes in the Zag phase, so if you make something which is time varying so that the Zag phase changes in time, then then you'll see a current. So you can see, so the time variation of the Zag phase is a physical current, but more generally, with appropriate, careful definition, one can relate Zag phase to electrical polarization, and so that's the closest to the physical observable that one can think of. There isn't a response function of the same type.
And maybe just a very basic question. So how does this chiral symmetry act on the model, like defined in terms of these orbitals A and B? Is there a simple way to understand that?
So I'm not sure how to directly answer. I mean, it's connected. It's essentially, it's related to. It's guaranteed by the fact that A orbital is only coupled to B and B only coupled to A. So if you have all of these chiral symmetries can be viewed in a block diagonal form, where there are there are A-type and B-type orbitals that couple, and there's no direct coupling from A to A. And so I don't have a ready answer about transformations, but the underlying physical relevance is that we have some off-diagonal structure. Here it's very simple. It's just each block has got dimension 1, but more generally it guarantees that you can bring it into a block diagonal form.
Sorry, isn't that the symmetry of the spectrum between up-down?
It leads to, yes, it does. It gives you a spectral symmetry from energy plus to minus. But in terms of transformation on the wave function of the states,
okay.
But
yeah,
but indeed it gives a spectral symmetry,
yes.
Which is about. I'll comment.
Also, the Berry phase is 0 when you have time reversal invariance.
So say what is?
The Berry phase is 0 when you have time reversal invariance.
Well, this has.
This is not time reversal invariant?
No, this is time reversal invariant, but it doesn't mean, so the Chern number is 0.
Chern number is 0.
But the Zag phase need not be.
Yes, the Chern number, yes.
The Chern number is 0, that's right. But this also has time reversal symmetry and particle, this has lots of symmetries, but it still gives you a non-zero Zag phase.
Naively, I would expect a symmetry in switching A with B.
Symmetry?
Yeah, I mean, of the spectrum. So why there is this asymmetry, no? J larger than J prime and J smaller than J prime.
Oh, it's a good question. So there's a, I've made there's a particular choice that I've made of calling what my unit cell is. So I associated these two with being my unit cell, and I called that unit cell labeled J. And then I had another A and B, and I called that, J plus 1. So actually, everything I'm saying is predicated on the notion that my unit cell is defined in this way, and so therefore, the line that goes from A to B to the right is within the unit cell. So that's what I had called J prime. So J prime is within the unit cell. Now, if I were to make another, I could make another representation of a model of this type where I choose to associate B and A with my unit cell in some other, and then I would get, what I call Zag phase pi and 0 would be different. So that's, and so that, you say, well, which one is topological, which one's non-topological. And where it really becomes crucial is when you ask, what are the physical consequences? And the physical consequences that I've emphasized are about the existence of edge states. And where we have an edge, it depends on how we define the unit cell. So if I have an edge, imagine I have an edge that terminates with an A on the left, then it's natural to describe the properties here, I should work in the case where I have my unit cells of this type. Whereas if on the left I have an edge which finishes with a B, then it would be natural to work in these terms. So there's an ambiguity in the real space. If I have a real space lattice, how I choose to represent it in this mathematical structure, there's an ambiguity, but that ambiguity is always resolved by the physical questions that we try and answer, and so that's how it would appear in this case. Yeah, thank you.
Yeah, excuse me. So I'm wondering, can we extend this Zag phase to higher dimension? For example, I mean, in 2D there are also sublattices of two kinds, right? Or some Lieb lattice or something, I don't know.
Yes.
So is it possible to repeat the same construction?
So you can construct the Zag phase in the Zag phase you can use to characterize band structures in any dimension. It's as a line integral across the Brillouin zone. Now, whether it can be used to construct a topological invariant or not is less clear. And it's here in one dimension. This is the only thing we have available. In higher dimensions, the actual topological invariant, maybe you can construct one out of some set of Zag phases, but it's you can always define them, and it's whether they connect to a topological invariant or not is something that's less clear. Let me quickly, in the last 5 minutes, I just say a couple of words about the physical consequences, and in particular about the gapless states. But let's imagine, okay, so I'm going to take something like this, where this is going to be J is 0, and there's nothing to the left. So I cut the edge, and then I have something of this type. Okay, so the physical consequences are that there are gapless edge states. And I'll leave it, I'll leave it as an exercise. If you take this situation where you've just got no hopping beyond here, you can show, it's relatively straightforward, an exercise to show that the state UAJ, UJB is proportional to minus J prime over J to the little j 0 has exactly 0 energy. And so this is a state where if J prime is less than J, this is exponentially decaying, so it's a normalizable state. So for J prime less than J, it gives you an edge state. If J prime is greater than J, it's exponentially growing. It's not a valid state localized to the edge. So you can show that you have an exact edge state, and you can just construct it analytically if you with a few lines of algebra. And just to give a bit of intuition, it's helpful to consider the limiting case where I take J prime 0 and J non-zero. Right? So this is continuously connected, to the case where J prime is less than J. I can just make one of them 0, and when I do that, then I have A, B. So the bond between A and B here has just disappeared. So I have an isolated site A, then BA, and then BA, and so on. And this is just disconnected site. It's the gapless edge state. Or it hosts a gapless edge state, because whether I put a fermion there or not just costs 0 energy. Right? It's just disconnected. It's kind of trivially a gapless edge state, but it's continuously connected to this edge state we have here. establishes the existence of this edge state in general. Whereas if we have the other way around, j equals 0, then we would draw this, with where everything is connected and there's no gap. Okay. And the continuity between these, is it's helpful to think that we could just adiabatically change the Hamiltonian and continuously go from one to another. Essentially, the special thing is that we're guaranteed to have an E equals 0 state, provided provided the Chiral symmetry is preserved. And the way to argue this, which again I'll leave as for you to think about or as an exercise, is to use the result that Andrea mentioned, which is that if you have chiral symmetry, then you can show that the spectrum is invariant under E goes to minus E if you have this chiral symmetry, sigma z h sigma z is minus h. And then if you have a state, like this one, which is sitting at exactly 0 energy, you know that if you introduce any perturbations which preserve chiral symmetry, that state can't go away from 0 because there's an isolated state at 0 energy. It can't move up, it can't move down, so it's stuck at 0. And one last remark, just to make connection to the entanglement spectrum. I said before, and again, in interest of time, this is going to be an assertion, and you can separately calculate it if you wish. Let's imagine that we have, think about the entanglement. And now we have a bulk system, A, B, so there's no edge. We're calculating the entanglement spectrum for a bulk system with no edge. But let's take these limiting cases again, like this one where J prime was 0, and we only had a bond between those two, and then so on. B, A, and so on. And in this case, if we take our entanglement cut, which of course should cut between two unit cells, so it cuts across here. So under the entanglement cut, you can check, well, it cuts just one, there's one fermion that's delocalized between A and B, right? We just have, there's one fermion that's sitting in a superposition of being in B and an A on this bond, and you can check that the entanglement spectrum, the full entanglement spectrum, has a twofold degeneracy. It has a half, and then lots of zeros. So it has an exact twofold degeneracy associated with this fact that the spectrum has got a gapless mode, and that gapless mode gives us a degeneracy. Whereas if we had the other case, J equals 0, J prime not equals 0, then we have A, B, and so on. And our cut, the system is completely separable where we make our cut between unit cells, and so the entanglement spectrum for the separable state is just trivial. It's just 1 and then lots of zeros. There's no entanglement at all. Okay, well, I think I should. I'll stop there, and so that's everything I want to say by way of introduction to the notion of symmetry-protected topological states, at least for free fermions. And next time I'll go on to start thinking about time dependence. First about adiabatic time evolution, and then more dramatic Floquet and quench dynamics. Okay, but I'm happy to take questions if there are. Ah, yeah.
As you wish.
Now there is a guy who is trying to start the alarm system, and so there will be an alarm ringing for a couple of minutes.
Ah, okay.
Okay.
So,
We take a break of 10 minutes.
All right, so yeah, there's a problem with the alarm here apparently. So we cannot take questions right now, but discussion session just afterwards. So we recombine in 10 minutes, and let's thank Professor Cooper.